So to start, an apology. I'm very sorry to all of you. This talk will not be about generative AI. I know that's the main topic of this conference, but I'm kind of an outlier here. So the first question you may have is, well, why? Why do you bother to talk about something that is not as hyped as generative AI? Well, that's because Gen AI works very, very well with pictures, with videos, with audio, with text. But still, some of the most crucial data sets out there, some of the data that power the world economy is not text, is not pictures, is not video, is not audio. I'm talking about data sets in the financial industry, data set in energy, data set in space. Like I've seen here, there is some people from the space industry that works with satellite telemetry. No way that is going to be transformed into text. And if we want to work with tabular data, then we need to have good tools, and we need to know how to use them. As everybody of you that has tried to develop a machine learning model, an old good one about predictive AI, not just a system based on foundational models, knows that most of the value is not unlocked by the model itself, but it is unlocked by the data transformation that come before. So today, I would like to spend the next 23 minutes talking about one of the most modern tools in order to transform data set and prepare your data for a machine learning model. So let's start from an example. Here we have a very famous data set. That's part of the Diamonds data set that comes with the ggplot2 R library for the guys who tried R in the good old days. And that's a very common example of tabular data. You have different types of columns. You have integer columns, categorical columns, and real valued columns. You want to make some transformations on this data set. For example, you want to filter only the diamonds that have cat equal to ideal and that weight more than 0.2 carats. And then you want to compute the average price by color. This is some Pandas code that does the job. It works, but it has a couple of problems. For example, how can we optimize this query? Assume that the dataset is not 54,000 rows, as this dataset actually is, but 54 million rows, or 540 million rows. Then just executing one step after the other is not the best option we have. And what if the dataset is so large that does not fit onto the 32 gigabytes of RAM that we have on a commercial machine? Should we just raise the white flag and go straight to a Spark cluster and spend like 2 weeks trying to spin it up? Maybe not. Maybe we have some middle ground that may work in real-world situations. Enter Pandas. Pandas is a next-generation data transformation tool. It's not that Pandas is bad, but Pandas was built in 2008, when computer vision was not solved yet, and when things like LLMs were just science fiction. It is today a technology of the past, not because it was bad, but because the technology has progressed. Pandas is written in Rust. It is based on Apache Arrow, that, by the way, in 2008 did not exist. It works with native parallelization at a low level. The parallelization is not implemented in Python, but is implemented in Rust. And by chance, it has a syntax that is very, very similar to the nice and elegant syntax of dplyr and tidyr. When Richie Vink, the inventor of Pandas, was interviewed on the topics, he said, I didn't know about these R libraries when I first wrote Pandas, but they indeed are super similar. So because of these features, Pandas is super fast, and it has a very smooth developer experience. Pandas has basically 3 main operating modes. We will check out all of them today. The eager mode is the easiest one, and it works like this. You read a dataset from some source, you perform a series of transformation, and you store everything in a data frame. This is not different from Pandas. A data frame is a data container structured in a tabular way. And when you write a query like this, each step is executed one by one. So if you do like this, then basically you gain nothing. It's exactly as the query I've written before in Pandas. You cannot optimize it. I mean, you can optimize the single step, but you cannot optimize the whole query because, again, it gets executed one step after the other. The code is not declarative. The code is procedural. And if the dataset is larger than the physical memory of the computer, you get an out-of-memory error, and that's it, basically. What you get is a better API, a better developer experience, and there are some very smart tricks hidden under the hood in the Rust implementation, or even at a lower level in the Apache Arrow implementation. In fact, Apache Arrow is, before everything else, a standard to store data in the memory of the computer. And this standard has very nice optimizations. For example, Arrow arrays are stored into buffers. Buffers are contiguous areas of memory, like C arrays, for example. And each numerical arrow array is split into 2 buffers, a data buffer and a series of validity bits. You can think of validity bits as flags that highlight when a value is not available, right? This feature is super handy because it allows for fast vectorized operations. You can process the data that is stored in the data buffer using the vectorization of modern CPUs, and you can process the validity bits using the same primitives. Sure, you may do more work because you may do useless operations for values that are, not available, but you do not break the pipeline of instruction at the CPU level. This makes operations much, much faster at an hardware level. And still, this is not at Arrow level, but it is at the level of the Rust implementation in Pandas. There are some smart tricks to optimize the most common data processing operations. For example, assume you need to implement a group by operation at low level. What can you do? Well, of course, you leverage hash maps. So you leverage the same data structure that powers Python dictionaries. But you want to parallelize this operation because at the last level, you want to exploit multi-threading. The simplest thing you can do is you break data into chunks. And for each chunk, you create an hash map where the key is the group and the values are or the data in the other columns, right? So if I group by X and I want to find the average of Y's, I can get hash maps like this. In thread 0, we have the key A and the list that contains only 1, and the key C and the list that contains 2 and 3. In thread 1, we have a similar data structure. But then we get into a problem because we have the key A both in thread 0 and in thread 1. And so what we need to do when the parallel operations are done is to synchronize the threads by rebuilding the hash table. This means allocating memory every time that we get a conflict between the same key being allocated in more than one thread. And this is very inefficient. What we can do instead is assigning keys only to one thread. Let's check out the other part of the slide. Here we can compute the modulus of the hash of the key modulus the number of threads. There is a typo there. It should not be 0, it should be 2. So if the modulus if the result of this operation is 0, I assign the key to thread 0. If the modulus of this operation is 1, I assign the key to thread 1. Of course, each thread needs to hash all the values in the group column, but then you do not need to combine the hash table. So you pay the price of a very, very fast operation that can be easily vectorized, not to pay the price of a much slower operation which cannot be vectorized. So the second approach is faster overall for large enough data sets. So these are just two examples of low-level optimizations that Polars gives you for free, because you do not even need to know that these things are implemented either at the Arrow level or at the raster level. But still, you get the two problems that I've introduced before. And how can we solve the first one? So how can we optimize the entire query and not just operation by operation? This solution was found many decades ago, and it implemented in every relational database. So DataFrame did not discover anything new. It just put the pieces together, as often is done in science and engineering. So the main idea here is do not write a query as a procedural series of steps, but as a declarative, unique operation that does not get executed until it is entirely written. And this means that Polars, in its heart, is not really a DataFrame library, but it's a query engine. It's an engine that optimizes queries with a DataFrame interface, because that's what everyone is used to, thanks to Pandas. What does this mean? When you write a query in lazy mode in Polars, what you're building is not a DataFrame, is not a data container, is not a table, but it's a LazyFrame, which is a graph of operations that are connected together. But let's do an example. This is exactly the same code as before. There are just two differences. The first line is not read CSV, but it's scan CSV, and the last line is collect. When you use the scan primitives in Polars, what you do is you create a LazyFrame. So no data is read at that point yet. All the data processing operations are only executed at line 9. That is when you call collect. And at line 9, you have the entire query. And this is the key idea. You do not do anything with the data until you have the whole query, so that you can optimize all the steps together. This is much more complex than executed step by step, than executing a query step by step, and involves the query to pass through several layers of optimization. In Polars, a query is first written in Python, then it's parsed into an intermediate representation that we will see in a moment. From the intermediate representation, a logical execution plan is drafted, then it is optimized, and then it's translated into operations that are performed at the hardware level. This is exactly what happens in every relational database, by the way. Nothing new here. This is decade-old research. And so when Polars developers had to implement this, they had lots of literature to build upon. So if you want to reproduce this example, there is a repository in the end of the talk. There is also live coding that I will not have time to do, actually. But still, you can not run the collect, so you can avoid touching the data, and you can run the show graph method on the LazyFrame that shows you the query execution plan. If you do it with optimized equals false, so please, Polars, do not perform any optimization, which is the very stupid thing to do, but we will do it anyway, you will see something like this. So from the top to the bottom, you scan the CSV, reading all the columns. Why? Because we are stupid. Then you filter, then you perform the group by, and then you sort at the end. This is exactly what I had written in the query. This is not the best way to do it. If we allow Polar to do its job, so to perform the optimizations, the graph is much different. So we scan the CSV, taking out only 4 columns out of 11 because we do not need the other ones, and filtering at the disk level. So if we have a CSV, filtering at disk level means still reading every row and just loading the relevant ones, but you still have to read all of them. So at least once, they all pass through the memory of the computer, which is inefficient. But if you have a much better data structure, for example, a parquet, you can only read the metadata and read only the rows that you care about. So huge optimization right there. And then after you have pushed down to the read operation all the projections and the filters, then you can run the group by and the sort. That's not the only optimizations we have available. We have all these lists, and all of them are executed by Polars automatically without the need for us to change anything in our code. The only thing we have to do is not to be stupid and not to set the flag optimize equals to false, which no one is doing anyway. What are these optimizations? Well, we have seen the most important of them. So the filter and the projection pushdown. It means that filters and column selection get done at the first possible step in the query execution plan, so that we actually process and load into and keep into memory only the data we really need. Then there is expression simplification. The 2 expressions right there are exactly equivalent mathematically, but in the first case, I have to multiply by 10 every element of a column, and if I have 1 million element in this column, it's 1 million operation for no reason whatsoever. In the second part, well, I only have the comparison to do, which I must do anyway. So 1 million operations saved just with a simple mathematical division. The last one I wanted to talk about is subquery reduction. If you have very complex queries, chances are that the same part of query gets repeated multiple times. Why do you need to execute it multiple times? You don't. So what you do is you change the graph that represents the query, again, without touching the data, to execute the operation only once and caching the results. This is, by the way, also what TensorFlow does in its graph processing, TensorFlow and PyTorch, both of them. Then, when all the optimization is completed and you are down to the physical plan for the query execution, you materialize the data into a data frame. So all the processing gets done into a LazyFrame, and then the data frame object is just materialized when all the optimization is done. This is, again, not something new. If you have ever tried to use Spark, not great, but if you have ever tried to do that, it's exactly the same thing. All the queries are created as DAGs, directed acyclic graph, and when you collect, the data are materialized into data frame-like structures. Again, the way you store the data matters. If you have CSV, there is absolutely no way for how the data is memorized on disk not to read every line. You have to read every line anyway, even if you push down the filters, even if you push down the projections. If you have parquets, what you do is you only read the metadata, and then you only access the data stored in the disk that you need, because the metadata point you towards the right sections of the files you can read. So use Parquet whenever possible. Now, whoa, I'm not late, great. Let's talk about the last great tool that Polars gives you for free is the streaming engine. While query optimization is basically stable, the streaming engine is being completely rewritten by the Polar code developers. So you're going to have a different engine in a few versions time. And this tool solves the problem, what if the dataset is very large, so large that it does not fit into the physical memory of the computer? Well, the solution, again, is not new. It has been known since a lot of time. The idea is not loading the entire dataset in the physical memory of the machine, but to split the dataset into chunks, process each chunk separately, and then store each chunk separately into the destination of the data processing. Can you do it always? No. You can do it only if you do not have operations that require the full dataset to be computed. For example, if you have a cumulative sum, tough luck for you. If you have a sort operation, again, tough luck for you. You cannot use streaming mode in this case. Again, the syntax is very similar. The only difference you must do is when you call collect, specify engine equal streaming, or when you write the data, do not use the write operations, but the sync operations that support streaming mode. Again, remember to use scan at the beginning to build the LazyFrame, otherwise the data gets taken into the physical memory with the read operation. So if you want to use streaming mode, scan to read and sync to write, or collect with engine equals streaming. So let's see the graph, the execution graph at physical level of this query. What we do is, again, run all the optimizations and put the projections and the filters at the lowest possible level. Then we do the group by in streaming mode. Group by can be computed in batches, so we do this into batches, and then we fall back to the in-memory engine with the sort, because we need all the data to do it. Be careful, because Pandas does not give you any warning when it falls back to the in-memory engine. So if you run this query with engine equals streaming, it gets run in streaming mode up until line 8, and then it falls back silently to the in-memory engine. So if you still get an out-of-memory error out of a streaming query, just check the operations that you are performing, because Pandas will not tell you. There is a very important parameter about streaming mode, that is the chunk size. It means how many rows should I put in every chunk. Pandas allows you to set the chunk size if you really want, but by default, it gives you a reasonable value. And this value is computed with an heuristic. Here is the code, which I've actually taken from the last source code. Pandas is open source, so you can do it. You can go to the Pandas repository, scan through a bunch of Rust files, and get the source code that actually implements this heuristic. And the idea is, apart from the constants that are kind of arbitrary, if you have more threads, then you need smaller chunks. If you have more columns, then you need smaller chunks, because the constant that represents your constraint is the physical memory of the computer. So if you have more threads, and so you can process more batches of data in parallel, then each batch should be smaller, because otherwise the memory will be filled up. If you have more columns, so each batch is actually larger because you have more columns, then you need to decrease the number of rows, again, because you need to respect the constraint of the physical memory, otherwise you get an out-of-memory error. Is this heuristic always perfect? Hell no, because Pandas does not know which machines you're running on, does not know exactly which kind of data you're working with. There is in roadmap the idea of improving these heuristics, but still, probably the best thing you can do if you really need to squeeze every bit of performance out of your pipelines is go with trial and errors and optimize this value manually. So this is an example of a query completely run in streaming mode. There is no sort here, so all the operations are parallelizable, groupable. You have the scan at the beginning, you have the sync at the end, and so everything is run in streaming mode. If you want to check it out, you can take this code, you can run the showgraph method on the query, and you can check it out that everything is run in streaming mode. Okay, I'm 20 seconds late, so I'll just point you out to the repository where I had the live coding notebooks. They are Merimo notebooks. Merimo is a great tool if you want to check it out. And I'll just leave you by saying that I'm Emanuele Fabbiani. I'm an AI engineer at Extreme and a university professor at the Catholic University of Milan. I enjoy traveling through Europe at events like this one, talking about the things I like doing, like processing data, and the same at several universities around Europe. That's it. Thank you very much.
Thank you. So in streaming engines, we normally talk about unbounded windows and aggregate windows. Is that a
Say again, sorry?
In streaming engines, we often talk about unbounded data streams where we have moving or hopping windows. Is this a similar concept here, or is it streaming mode only supporting data sets of fixed size?
If you talk about real streaming mode in which data are arriving one after the other, no, Pandas is not built for that. If you are looking for something like Spark streaming, there is nothing like this. And there are no plans to build it as well, so no. Oh, by the way, this is not phishing, it's a QR code to my LinkedIn profile, if you want to connect.
Thanks for the talk. In my workloads, I'm usually dealing with partitioned data in Parquet stored in S3, and I usually use the Dask for processing, prefiltering, and gathering to, all in the Pandas as the end. What props do you see of using Polars for the same scenario instead of a Dask?
Okay, that's a very good question. I do not know the answer because I've never worked with partitioned data. But I think that the answer is can be found just by looking at the scan Parquet method and see if it, yeah, you have some kind of support for partitions here. So I'm not really sure how to elaborate more on this answer because I've never tried. But still, something is there.
We are getting a bit late, so maybe we can keep them, because I see several questions, so we will not be able to take them. So let's thank our speaker again.